Good afternoon, everyone. Welcome back for more of the last day of Hope 2020. Before we jump into the next talk, we want to send a big thank you to all the attendees, presenters, and volunteers whose commitment to hope and to our community have made this event possible in these difficult and trying times. So next up, we have Zack Freedman. Zack is a freelance prototype developer in New York City, building electronics under the name of Void Star Lab, and has a passion for wearable technology. His talk today is titled Disgusting Secrets of Real Hardware, and it's on how to clean up the filth and improve your own designs by closing root shells, plugging back doors, locking down firmware, designing defensively, provisioning secrets, and more. He says you'll walk away a bit savvier, a bit more prepared, and a bit more disgusted with your favorite electronics. Remember, we'll have a Q&A session with Zack after his talk, so be sure to submit your questions via the Metrics chat window, and we'll feed them to Zack so that we can hear what he has to say. Now, over to you, Zack. Take it away, ground control.
Good evening, Hope attendees, and good whenever it is, YouTube people. I'm Zack Freedman, prototype developer, and today we're making fun of some electronics. Welcome to my workshop in the beautiful West Village of New York, New York. Don't listen to the president. The city is not being sacked by barbarians. That's me wearing an eye tracking headset I built, and this is my workshop at the Fat Cat Fab Lab. The original plan was to throw an all-night party here at the Fat Cat, but no! This viral bastard just has to invade our alveolar cells and ruin everything. I am digging this whole, hope over the internet thing. I definitely miss all the late-night shenanigans, but damn, there are so many excellent speakers, and we've got all the time in the world to listen to them. For maximum immersion, I've brewed my own mate and ran it through the soda stream, and it tastes like crap, which means I succeeded. Alright, let's talk about filthy hacks. How many of you have ever busted open a piece of electronics to do a hardware hack? How many of you have built electronics yourself from the ground up? How many of you know that I actually recorded this a week ago? All right, I've been building electronics for about a decade, and I've been a freelance prototype developer for around 8 years. I do a lot of engineering, but I'm not an engineer. I got my degree in business and technology at Stevens, and I taught myself all the programming and circuits and stuff. I built a lot of projects for clients and myself, my data glove, my eye tracking headset, and a PC case mod that endlessly generates fake boot text. As a professional prototype developer, I build things like concept hardware, art pieces, custom projects, and even the occasional product. My clients are satisfied, but I used to get awfully insecure about my work. My projects were made of copied and pasted reference designs, Arduinos, running off-the-shelf libraries, modified example code. I just didn't think that real engineers, like the ones that look like this, would consider my designs to be professional quality. I was a little terrified that one day a client would send my work to a real engineer and they'd shoot them an email back and say, did you pay that jabroni? Or maybe I'd forget to close some crazy security hole and some Russian hackers would pwn the crap out of it and it ends up on the news and somebody does some sort of presentation at a hacker conference about it. I really did stay up late tossing and turning. Because I left a labeled debug header in the release product, or I forgot to set a security fuse, or I made so many mistakes and none of my footprints fit the first time. And my heart would sink whenever a client sent me a picture like this. And I panicked, how did I let this happen? How could I have caused this? Time went on, and I got more experience. I saw other people's projects inside and out, warts and all. I tore open products to modify and reverse them. I read news stories, I sat through talks, I listened to podcasts, swapped stories, and it turns out many of those bonehead design decisions that I bumbled into are not unique. Many of them are actually very common or even industry standard. So today we're going to rip into real hardware that's been really released into the real world and discover filthy engineering. We are going to see just eye-rolling levels of sloppiness, laziness, corner cutting, short-sightedness, and creativity. Before we begin, we're going to do just three points of context. A, just because something is disgusting doesn't mean it's bad. Most of what I'm going to show you is deliberate and came from calculated decisions with reasoning behind it. A lot of these things were done on purpose with intent. Engineers are generally diligent and good at their jobs, and it's usually the business realities that sully the product, not anyone being a smooth brain. Point B, I really wanted to use my own projects here, but my clients are not okay with me walking randos through the security flaws and mistakes I put in there. Most of the examples are going to be authentic mass market hardware with pics from sites that are okay with me doing such a thing. Finally, I'm not a cybersecurity expert. I am a prototype developer. My job is to implement the security flaws, and I don't really know that much about exploiting them. I'm not purporting to be any kind of security expert, so I'm going to take the academic approach. Specifically, I leave the pwnage as an exercise to the viewer. Okay, so all that said, let's get rolling. When you think of product design, you might think of a racially and culturally diverse group in comfortable but sensible attire, writing on whiteboards, annotating tablets, and rotating things in 3D. But okay, you probably don't, but it is safe to assume they at least, have meetings. Or at least the guy designing the enclosure to hold the circuit board and the lady designing the circuit board itself would work together. Well, no. Pretty often they work for different companies. Most companies don't have in-house industrial designers or mechanical engineers. They engage a design firm and mechanical engineers to sculpt the physical stuff or pick a model off the shelf. And then the engineers design the PCB to fit. The EE, in fact, might be an independent contractor themselves, like myself. Electrical engineers are often left out of the high-level design process. Instead, they get an email with, hey, fit a workstation PC into this. Okay, thanks, bye. And you got to make something that looks like this. Weirdly shaped boards are awkward and they're ugly. They're harder to design, they're harder to produce, and they're ugly. They also affect performance. They emit more noise, and time goes from improving the design in the schematic into cramming all those components into that bizarre profile. Really thin, tiny, and irregular boards flex more, and they need special programming fixtures and production steps. But they make the design look sexy, and your boss doesn't have to pay the engineers and the designers simultaneously. So, here's another example. Look at this pocket-sized benchtop power supply. This poor bastard had to cut this giant hole in the ground plane so that it didn't get in the way of the wireless antenna. And by the way, look how the module is only supported on one end, like a tiny diving board. Look at that control board. It had to be made of 2 scraps of PCB swaged together because those mounting bosses in the corners are too big for the main board to go all the way to the edge of the enclosure. And as for those weirdly shaped cutouts and that strange board shape, that's there because the other board needs to pass through that board in order to fit that enclosure. Just look at this. Noise in a power supply is usually considered a bad thing, but the priority here was making it look like this. Here's another example. This is a speaker from IKEA. Just take a look at this board. Here's the Bluetooth audio bit on a daughter board, and the audio it receives needs to make it all the way across the audio it receives needs to make it all the way across the board around that cutout to the speaker. Why does it need to do all that? So that you can ram a cork through this hole and stand it up. Aesthetics. You know where Nest thinks the best place to put a battery is? Literally in the middle of the sensor. Just look at this board. Just look at it. Last example, cameras. Cameras are the absolute worst because people expect them to look and feel like 35mm film cameras from the 1960s. So boards are jammed in wherever they'll fit with ribbon cables snaking around, components everywhere. Just look at this. Imagine designing electronics for this. You have to cram your super advanced image processing and digital signal processing chips onto a board that looks like a subway map. I also like how they put this heavy-duty insulating boot around this massive capacitor, but they use this super fine-pitch connector with no creepage, so a speck of anything conductive would short it out. Nice. So every electronic component has a data sheet. This is a document written by the manufacturer that explains how the chip works, its specs, tables of stats, what the package looks like, etc. But it also includes this, a reference design. This is sort of like a ready-to-go schematic. It's a schematic that implements the part that the manufacturer has tested, where each of its features are ready to use. Manufacturers sell evaluation boards and developer kits, and third parties sell breakout boards, and all of these usually implement those reference designs. These are extremely useful in the early stages of product development because you're starting with known working vanilla schematics. You don't need to engineer all that yourself. You can buy them pre-implemented and just chain the boards together for testing. You combine that with some open hardware that's easy to program, Arduinos, etc., and off-the-shelf modules for complex stuff like wireless, and you can jump right into prototyping without having to start from scratch. The product development process ideally looks something like this. First, you slap a bunch of pre-made schematics together to sanity check your idea, refine the specs, and really focus in on your business logic, what the thing does. You then put everything on a big roadkill board that has lots of open room so you can make adjustments and really, perfect that schematic. Finally, you take that and get it into the correct form factor, and that's your prototype. You trim unnecessary features, you add protective components, you tighten up your design, you replace these expensive modules, you solve problems, and you'd think that by the time you're done, very little of those off-the-shelf modules and pre-made reference designs would remain in your finished product. I mean, it's not even like you're going to take your prototype straight to production, right? Well, the boss sees that the prototype works fine, and DFM ends up being cut 25% off the bill of materials and goes straight to the contract manufacturer. So things that you put in early in the process to speed up your development end up making it all the way into the finished product. Here's an example. This is my desk, and it features a 5th generation ErgoDox mechanical keyboard because I'm a giant nerd. The left side is suspiciously similar to an MCP 23018 I/O expander reference design for driving button matrices, such as the ones in mechanical keyboards. The right half of the keyboard is literally an Arduino Leonardo. That design I was showing you earlier, that was a car stereo mod that I designed for a client a while ago. It's an LM358 amp reference design, combined with an AP6502 switching regulator reference design, and literally an Arduino Uno. It's a bunch of off-the-shelf circuits, and goddammit, I am proud of how well it did the job. It's tempting to think that only small-time outfits would build projects by copying and pasting, but that is just straight not true. This is an FBI tracking device that Kathy Thomas, an environmental activist, found stuck to her bumper. It's made of 2 stacked boards. The top is a U-Blox all-in-one GPS transponder module. This was cutting edge in 1999 and has a very helpful datasheet. The bottom board has a ZMix 3 to 500 megahertz transceiver chip and an RFM RF1172 filter, and both implementations look an awful lot like the reference design. Actually, it looks like the FBI did change the design a bit. On the top side, it looks like they added some capacitors by hand. I just love the idea of some lantern-jawed FBI agent, black suit, sunglasses, earpiece, just delicately blowing away flux fumes as he soldered this up. Implementing reference designs is a lot like copying code from Stack Overflow. We pretend we understand it, we hit Control-C, we hit Control-V, and then we make pre-recorded conference talks about how good we are at engineering. Implementing reference designs, or at least starting out with them, is usually a good idea. There are design engineers at these companies, like real humans with personalities and families that make these things. These guys are often friendly and will help diagnose issues in your implementation. Some datasheets have sleazy reference designs that recommend specific parts from companies that they have relationships with. Or they even recommend their own parts, especially the expensive ones for some reason. Why sell a chip when you can sell a solution? The point is, reference designs and breakout boards are starting points. As a rule, they are not ready for production, and it's up to the engineer to find out why. Good engineering should require rigorous testing on the bench and in real life. I mean, after all, when it comes to breaking stuff, the user outranks the engineer. It's up to everyone to find out where those reference designs fall short and don't get too overcommitted to them. It always makes sense to use the right part even if it's harder to develop over the long term. Speaking of testing, as of 2020, electrical engineers are still incapable of jacking into their electronics projects. I consider this a grave oversight, and instead they add debugging interfaces to upload and diagnose software and to snoop on critical signal lines and other critical paths. By the way, this right here is the best slide in the deck. I wanted a picture of a guy in a VR headset messing with a circuit board, but the best I could find was this guy messing with a whiteboard, and he's drawing a cat. I know because he wrote cat. Anyways, the next best thing to jacking into your circuit board, besides jacking into a whiteboard, is adding a debug interface. Some of these things, like these SPI headers, just expose the lines of communication between the microcontroller and its peripherals. These make it really easy to connect logic analyzers and scopes, and they can also be used to upload firmware. Other ports are dedicated specifically to the software, to diagnostics and programming. This is a JTAG header. Don't worry about the acronym, because it's basically a programming interface for a microcontroller. It also provides access to debugging tools like setting breakpoints, which doesn't sound impressive if you're used to writing real programs, but trust me, this is hot stuff on a microcontroller. Anyways, using this port, you can burn new firmware onto the device, extract the existing firmware, snoop the memory, and just generally do all kinds of handy low-level debugging functions. You can order microcontrollers pre-programmed, and this functionality is extremely dangerous, right? So it makes sense to remove this header when you go to market, especially if it's one of these fancy headers that just accepts this convenient spring-loaded programmer. Otherwise, somebody could say, take your commercial off-the-shelf hardware, jab a convenient spring-loaded programmer into that header, suck out your firmware, steal your secrets, modify your firmware to make the device catch fire, and re-upload it. In the past 70 years of electrical engineering, real engineers trademark have made many powerful anti-tampering countermeasures. You have access prevention, write-once fuses, code signing, and code integrity checks. They're increasingly common and easy to use. That said, I don't think I've ever used them, and I don't think I've ever met anyone who used them. You might think that it doesn't get any more nauseating than a convenient unsecured port with firmware access. So allow me to direct your attention to this little bastard. This is a serial port, and it's even more common than a JTAG header, and in my opinion, even more dangerous. All serial ports have at least 3 pins. You have a receive, a transmit, and a ground. If you've ever used an Arduino or you had a computer in 1995, you might have heard of a serial port, and that's exactly what these are. What's neat about a serial port is that they're often used to communicate with humans, not complicated devices, and they communicate in plain text. All you got to do is get a USB to serial adapter, and you could barge right in. This is an FTDI basic from SparkFun, and I highly recommend it, but there really are like a bazillion USB to serial adapters out there, and they do the same thing. I keep all mine in an Altoids tin so they stay fresh. Asynchronous data, collect the whole set. It's really important, by the way, to first use a multimeter to figure out what voltage it is, because you connect a 5-volt 5-volt serial adapter to a 3-volt device, and you're going to need a second device. Anyways, you just look for 3 to 6 parallel holes on the board, and that's probably a serial port. You'll often find multiple headers on a board if the device has multiple microcontrollers, which is increasingly common. One of these holes will have a little starburst around it, or like an extra thick trace where it connects to the ground plane, and that's your ground. You might need some guesswork to find the receive and transmit pins. That just comes down to try out the various combinations until something works. But sometimes you get lucky, and a friendly engineer will do you a solid and label it right there on the board. Debug headers. What do you think we'll find on this serial port? Does it stream maybe some debug logs, some core dumps, maybe some printf style status strings left over from development? Could it be a little bare bones command line to access hidden functions and factory diagnostics? Maybe it's an encoded channel for a technician to connect some super secret maintenance tool. Or maybe it's a bash shell with root access and a default username and password. And you bet your ass that's what it is. Every embedded Linux distro I know exposes a shell on that dedicated serial port. Usually that command line is root, because creating separate accounts with reduced privileges is hard. Usually the username is root and the password is root, or it's admin, or it's password. Some fancy devs change the password, and that said, I've never seen a manufacturer provision unique passwords onto the devices, even though they totally should. At best, they'll derive it from the serial number or MAC address, and if you can find that algorithm, you're in like Flynn. Many manufacturers will change every one of their passwords to the same password and then put that password into a manual that's available for download NDA free from their site. This is especially common for routers and other devices that should really be secured better than this. You might have been smart and like set your SSH server on the device to not use passkeys and only certificates, but you should know that this has no effect on the hardware serial port. I don't actually think you can set that to require a certificate and not a passkey. Anyways, like, you just take that device with crazy hard security, log in, install a new private key, and you now no longer need to sneak into the boiler room to mess with the HVAC. This brings us to the filthiest crevasse of the embedded world. I must stop showing you pictures of circuit boards because this foul miasma is invisible. It's firmware and it's the libraries that these systems are built on. Trigger warnings, unpatched vulnerabilities, decade-old kernels, unencrypted networks, and literal fire. You guys are pretty plugged into security penetration, and you're probably aware that embedded devices are notoriously insecure. Not much has changed. In preparation for this talk, I went to Shodan, Rami Malek's search engine of choice, and I did a search for Dropbear. Dropbear is a super lightweight SSH server that's included with BusyBox, which is in turn included with most embedded distros. The overwhelming majority of these devices are running Linux 2.6. The latest version is 5.7, and I can't imagine how few of these have been patched for shell shock and all those other vulnerabilities we've seen lately. Yeah. This one was my favorite. This poor Canadian bastard's cable box is running Dropbear SSH version 2012.55, as in version 55 of the year 2012. The last time this guy's cable box was updated, Barack Obama was beginning his second term. There have been some security improvements since then. Here are some iOmega NAS devices that back up people's sensitive files. iOmega was kind enough to announce to the open web that these are NAS devices presumably full of sensitive files. These things support only TLS 1.2, which I have read leaves them vulnerable to the Golden Doodle variant of the Poodle attack. I don't know what the hell you guys are smoking when you name these vulnerabilities, but this is a device designed to keep your files safe and up to date, and iOmega's devs have made them unsafe by not updating them. But surely it's better in industry than it is in consumer products. I mean, these are devices that are going to be in service for decades, not something that you're going to like throw out when, I don't know, when Steve Jobs, I guess back in the day when Steve Jobs got on stage. Anyways, there are a lot of industrial control protocols used to coordinate heavy-duty equipment. These things have failovers, backups, and like other useful properties that come in handy when your software can kill people. Or if you've hacked a car, and come on, like it's 2020, who hasn't hacked a car? You're familiar with the CAN bus. There's also BACnet, which is used to connect like HVAC and building safety equipment. And you have the Modbus, which is used to connect heavy equipment in factories and processing plants and stuff. As a rule, these protocols are unencrypted, which isn't as bad as it sounds. Like if you're connecting a conveyor belt to the control console, like it's your own factory. You don't need to secure it that bad. It's not like you're hooking your industrial control equipment into the open web, right? If you have dubious morals and you want to control 40 relays in Romania, then you're in luck, my dude. See, the mistake wasn't putting the Ethernet port on the controller. The mistake was putting the other end of the Ethernet cable into a router. Here's another intriguing device in Castelnuovo di Sotto, Italy. What's neat about this thing, besides the fact that it's probably an Italian temperature controller that, shows up in a search engine, is that InventSense supplied the safety devices that were hacked in Saudi Arabia with that super advanced Triton malware. I'm not sure if this is the exact device we're talking about here, but you get the idea. You connect dangerous industrial equipment to one end, and you connect the other end to a direct link to everyone on Earth with a command line. Triton was this malware that disabled gas detection safety systems in a chemical refinery, presumably with the intention of flooding the facility with toxins. Through pure chance, it was caught and thwarted, but had it succeeded, Triton would have been the first malware with casualties. They really should have kept a better eye on these key switches. What's interesting is that in the Triton attack, they actually did prevent these things from connecting online, but they had poor internal controls. So somebody who got access to the facility was easily able to do a firmware attack and break that security wide open. Moving on, let's set some stuff on fire. Embedded devices increasingly have consequences. Like, not only are we sticking processors and everything, but we're hooking these processors up to more and more subsystems. This fire here was caused by a firmware attack. This USB power bank was connected to a USB-C quick charger. There's a microcontroller in charge, so to speak, of the charging subsystem, so that the device can demand as much current as it can handle. So this attack is launched on the Walwart by using it to charge an infected phone. The phone puts the charger into device firmware update through that USB port, and then it DFUs on a hacked firmware that instructs the power management chip to wait for the target device and then run 20 volts through it. This means that a malware attack can blow your phone up. Neat. It's a good thing that these Walwart manufacturers aren't just copying and pasting pre-written firmware onto an unmodified reference design. If they did that, the attack would hit tons of different devices from different manufacturers, and it would be a total nightmare to patch out of existence. Anyways, this is where we are. We cargo cult schematics, we leave all access debug ports open to the public. We deploy outdated software, we never update it, and we open it up to the internet. We connect more and more of the circuit to the hackable part, and we make ugly boards. These are just some of the disgusting secrets of real hardware. So, what do we do about it? I mean, as a rule, design defensively. The bad guys are going to buy some units, and then they have all the time in the world to bust them open. So don't make it easy. Clean up after yourself. Get rid of those debug ports. Prevent one part of the circuit from damaging another. Use fuses and thermistors to limit hackers' reach. Don't blindly trust reference designs. Force any bad actors to have to start desoldering parts. Get yourself involved earlier in the process so you have more influence on the look, feel, and configuration of the project. Don't put something online or even add provisions to bring it online unless it's absolutely necessary. There are tons of measures like intranet, private APNs, and just straight not putting a connectivity on it that can provide a lifetime of protection. And finally, use the anti-tampering devices that are already available to you. It's kind of a pain in the butt, but life sucks, wear a hat. As for the hackers, the makers, and the modders, don't be discouraged by how sophisticated and polished other engineers' work looks. That gizmo might look really sleek on the outside, but on the inside, it's just full of disgusting secrets, and they're waiting for you to unearth them. Thanks for watching. I'm Zack Freedman, and I really hope you've enjoyed my presentation and the entire Virtual Hope Conference. This has been a blast to research and record, and I really hope you guys have had a great time over this past week. Huge thanks to the organizers, especially Bernie, for letting me do this talk. And thanks, Brooke, for being a most excellent camera person. And of course, thanks to you. You keep hope alive through 2020 and far into the future. And I'll see you on the other end of this pandemic. And when we do, I got a cold beer with your name on it. You take care, folks. Oh. Now it's time for Q&A. I am going to now time travel into the future and switch to live mode.
Thanks, Zach. Those were some great tips, and it's a great presentation. So tell us a little about what got you started in the hardware design development space in the first place.
What got me started building electronics? So I had an internship, and I had a lot of free time in the internship. And I saw this Hackaday article about this guy made a heads-up display and a wearable computer. I'm like, this is the coolest thing ever. How hard could it possibly be? It was hard, but I just really liked finishing. I just really liked building stuff, and really discovered that I was pretty good at it. So I started a hackerspace, but for the record, you should probably build hardware for more than a few months before you start a hackerspace. But I just got so deep into it, enough people were coming up and asking me to build stuff that became a job. It was so. By the way, the hackerspace, they're still open. It's the Hoboken Maker Bar. I'm no longer a member because I moved to New York City, but I was one of the founding members. I wore this, janky heads-up display made of a coat hanger and a video headset to a meetup, and someone's like, "Hey, you look like you'd be interested in a hackerspace," and I'm like, "I don't know what that is, but yeah," and we started it.
Excellent. So some questions from the audience here. Are there any manufacturers you found are better than others in not attempting to lock you into a company-centric reference design?
Ooh, oh, this is an excellent question. This is a great question. Generally, the more specific, I guess the more specialty the manufacturer is, the more likely they are to make it play nice with others, simply because they don't manufacture a huge variety of products. Personally, I like anything made by Linear Technology. Like they make power like regulators and various power electronics, and they're really good about recommending high quality and low cost components. That's one of the ones that springs to mind. Generally, the more specific the part is, the more open they're more open and flexible their stuff is, I think. At the end of the day, though, like it's hard to fault I bully TI a little. It's hard to fault TI just because they make like literally everything. I think one particular offender is probably it could like maybe Microchip, if I have to sling a little mud, because they recommend parts that they recommend parts from companies they've recently acquired. I'm gonna leave it at that.
All right, another question for you. What is the most common component or circuit you've been told to cut from a design that you thought was a huge mistake to drop? So it depends on which stage. All right, so depends which stage of the design it is. The ones that are mistakes, they're often components that like sort of that protect against bad behavior, right? Like a reverse polarity diode to keep you from putting batteries in backwards, or protective components on what are some like Zener diodes and stuff on like plugs in case somebody like puts voltage into an output. And like the thought process is like no one's ever going to do this, but they do. And we find out about it very quickly. Generally, when I think something like this will happen, I will add a provision. So, like for the diode, for instance, I'll add a way for it to be bypassed, like with a short. I just do whatever I can to make sure that they can then add that part later once they come to their senses. The parts that should be added early that are not is a bit of a trickier question, and that is probably the right component for the job. A lot of the poor designs I end up working on come that way because oftentimes a founder or someone early in the project will be using parts off the shelf, like pre-made boards and stuff, and they will insist on using those exact parts through to the prototype or production. So end up with like a bunch of Arduinos and a bunch of breakout boards, a bunch of the stuff on the breakout boards. Things end up with way too many LEDs, which drain a lot of battery, and I have to explain that. Let's see. One other thing I could think of is when they downgrade the processor. Never let your clients realize that there are cheaper processors that have the same footprint that they can just drop in. Because you design around, having a certain amount of memory and peripherals available, and every once in a while I'll get a problem, and I'll be like, wait a second, why is AVR dude saying that the signature of this chip is different? All right, so we've got
a fun question.
Another technical question for you there.
I'm not a very technical guy. I hope I can handle.
Yeah, well, let's hope so. So how do you know that setting simple user password combos on serial are a human error or human laziness and not an attempt at something nefarious?
I guess think of the attack surface here. Like the nefarious thing is, did this person leave themselves a backdoor? If you want to leave yourself a backdoor, like, oh, my camera's running out of battery. Oh no. If you want to leave yourself a backdoor, like, why you would probably set a password that doesn't allow everyone and their dog to get in. Like, change it to 26 random alphanumeric characters and write them down on a Post-it note and take the Post-it note with you. Don't change everything to root. At the end of the day, though, you got like the golden rule: never attribute to malice what you can attribute to laziness
or stupidity. So from a manufacturer security standpoint, do you have any suggestions on how to ensure machines in the wild can stay current, or is it too often simply seen as an externalized cost?
How to actually solve this problem and keep the devices current. See, this is actually a double-edged sword. One thing that I was considering putting in the talk, but kind of cut because it muddies the waters, is that the method that you use to update the firmware is itself an attack vector. Like anything you can use to update the firmware, a bad guy can use to update your firmware. But that said, like, this is better to have. It's better to have a need. I mean, you're gonna need some sort of device firmware update system, but you want one that can do an atomic update, and you want one that has signed code. Basically, what these two mean is you want a firmware update system that downloads the whole package of firmware, attempts to upgrade, and if it fails, it rolls back. Otherwise, it's very easy to get your device bricked. And you want to use signed code. You want to use signed code because it provides a level of protection against somebody compromising your server. That said, once you need a mechanism, and the mechanism has to be hands-off. It has to do it on its own because users are not going to push the update button. It has to do it on its own. I would recommend, if possible, build yourself in a channel that can be used to push emergency patches. One solution I've seen that was very clever is at the time of when you're provisioning at the factory, you provision a number of keys, like let's say 5 private keys onto the device, and those can be used to sign high priority updates, which I thought was pretty interesting. But you do need a mechanism to provide it. Personally, the way I like to get around this is I like using Python to write stuff, and Python is just a bunch of scripts, and you can just copy in a new script.
So what sort of tamper resistance mechanisms would you say add the most protection?
I mean, the biggest thing is just take the goddamn debug port off. Like, a lot of these attacks are simply like somebody is opening it up because they're curious. They say, "Ooh, I see 4 holes in a row. I wonder what I can get out of this." Or they're looking for just a way to do damage. They just want to get into a router or something of the sort. This goes double if you're deploying the device en masse in institutional role. Like, if you're let's say you're Verizon and you're selecting the router that you're going to give to all of your customers, like, please don't make it something that's easy to reverse engineer. Past this, just not having an internet connection is another good one. Cutting the attack surface down, forcing someone to actually spend money, it helps. There are other more effective and more exotic systems. Like there are high security chips that have like ingress. It's not really ingress detection. I forget the industry term. Basically, they detect if someone's trying to suck the code off, and they blow themselves up. But that's massive overkill for a community or for a consumer product. On the whole, though, make life harder for bad guys, and just encourage them to move on to a different target. We have a couple of questions
on that. Make it harder for bad guys. Some question came in asking about, well, what about the open source model, right? What about open source software and hardware and making it easy for people to interact and tinker with things? How do you make that balance between that, security, avoiding attack vectors, and encouraging tinkering and improvement?
This is like I don't kind of pains me to admit it, but this is what makes pitching open hardware to clients difficult sometimes. They think it'll cut their security. Getting more eyes on the project is almost always a good thing. The main difference is that when you're making a project hackable, you want to make it easy to work with on a bench, hard to work with in Romania. Like you want a person who has the device on their workbench to be able to mess around with it really easily, but you don't want me sitting in Manhattan to be able to do all that messing around remotely. So this comes down to like provide like honestly, biggest thing you can do is just make the dangerous stuff opt-in. The Raspberry Pi Foundation, to their infinite credit, has disabled Telnet and SSH and forces you to change the password by default on their largest distro, which I am sure has plugged hundreds of thousands of security holes across the world. Honestly, like best thing you can do is another thing you can do is honestly like don't license the thing commercial, because you don't want people to take a system built for developers. It's very easy to hack and just copy and paste it into production, because they'll take all of those flexibilities with them. So forcing someone to do a little work is one possibility.
Like a hard copy left license.
Yeah. But that said, at the end of the day, open. I got to make this absolutely clear. Open sourcing and open hardware is always a net positive. You get more eyes on it, and it massively increases the chance that a friendly person is the first one to break in.
Excellent. What about dipping the board in epoxy? Someone asked.
Potting and conformal are ways to deter all but the most serious access. You often see these in military. You often see these in like military settings, automotive, and things like that. This is all right. So at the end of the day, nothing is going to stop someone who's really dedicated from getting in there. They can find a solvent that dissolves it. They can mill their way in. Their ways in. Where that works best is for devices where it's not practical for them to get another copy of. Like, it's great for an aircraft black box, because if someone's trying to reverse engineer the aircraft, it's unlikely another one's going to crash in their airspace. It's a little less useful for your device. It's one of the challenges with those is that it makes testing and provisioning harder, and it makes the whole process more expensive. I would say that if you already have a use for the other benefits of doing so, such as like weatherproofing, it's not a terrible idea. It's an expensive production process, and it also means that you can't do any sort of rework or refurbishing. That said, though, like in small numbers, I've potted projects before, and I've done some conformal before. Some of these some of these devices have another failsafe in the form of some sort of light sensor, or even an explosive charge that detects when the epoxy is being removed, and it destroys key parts, which is really cool. Anti-tampering mechanisms are incredibly cool, and there is very little reason for anyone of our caliber to worry too much about them.
Tell us more how the explosive charge piece works.
I'm definitely not an expert at this, but at the end of the day, it's just about, you want to destroy the element that has the secrets in it. Sometimes just in the form of literally like a tiny blasting cap, but other times there's a circuit that charges a capacitor generally if the light sensor is triggered, and then it sends high voltage through the part that you don't want to survive the process. Also, like back in the day, you had these like light sensitive EEPROM. I don't want to talk out of my ass.
So can you tell us something about commercial devices with COTS components, like find an Arduino or an ESP8266 in a device? Is that common?
Ooh, sometimes. If you find these like sort of hacker devices carrying over into like a mass manufacturing project, you don't see that quite so often because of economies of scale. But like, if someone's making like a few tens of thousands of something, the difference might not be that crazy. You see this in a lot of like Kickstarter type projects, that basically hardware that's put together with a small team and funded through bootstrapping, and not through huge investments, just because like they just at no point do they ever have enough money do this massive redesign effort for a low cost part. You are seeing, honestly though, now as Cortex and RISC-V processors, basically like now that you can buy the same process, sort of the same core from multiple different manufacturers, you see this less and less because code is becoming more portable and processors are becoming a little more interchangeable. Back in the day though, you saw a whole bunch of stuff. ESP8266 is a notable exception. The NRF52 as well. You find a ton of Nordic parts that are very hackable all over the place, just because they are both cheap and easy to work with. You don't really see Arduinos though, because I mean the parts are just kind of expensive. I wish I saw it more often though.
So tell us about the worst piece of hardware you've ever had the pleasure or pain to design.
I need to filter this by the ones that I think I can actually talk about because of non-disclose. Honestly, the funniest ones are the ones that I turn down. I get approached. I don't want to sound mean because like I get approached by a lot of folks with big ideas who just want to verify whether what they think of is possible. So a lot of folks want to make like flexible electronics, and I have to explain that a battery, you can't find a flexible or a transparent battery. Folks, I had somebody who wanted to make like poker chips that they wanted to make poker chips that could be tracked using RFID, and I had to explain that like you can't read a stack of RFID chips. Some things are just some people like. I don't know. I guess I could have prepared better by assuming people would ask me this question, but I definitely have some goofy ideas. I definitely have some goofy ones. I was approached early on. I was approached by a dance troupe who had a dancing robot that performed in their troupe, and the guy who knew how to program the robot had left, and they needed me to repair and fix this dancing robot. And I ended up having to program new choreography onto it. So I guess I've sort of made a dance. I built some projects with electron guns. Those were a little dangerous. There were some sex toys. One of the challenges of being like a consultant is that a lot of your stuff is under non-disclose.
All right, what about your favorite one? You know, the one you're most proud of that you can talk about.
Favorite project. So, I mean, my favorite project that I've ever built. It's probably this data glove that I built. I built this data glove, and it lets me draw letters in midair, and it uses a machine learning neural network thing to recognize it and type it out, so I can control a wearable computer with it. That was kind of cool. But honestly, I mean, favorite one was probably a Nerf blaster, just because there's just nothing more satisfying than tagging somebody 150 feet away with something you built yourself. And you just see that dart sailing over the horizon, smacking someone, being like, I printed that thing.
Excellent. We're coming up to time, but I want to ask you before we finish up, do you have any recommended resource for people just getting started in hardware? What would be those key things that you would point them to?
Biggest thing to do. All right. So 2 things I'd recommend. The first is jump right into a project. Get into a project, hit a wall, do a lot of work, figure out how to get past it, hit another wall. You will not learn faster or figure out what questions to ask faster. The other thing, don't trade time for money. When you're just getting started or when you're just making an idea happen, don't like order parts that take a month to get delivered, and just do whatever it takes to get the project done now. Enthusiasm fades, but a cool project lasts forever. And finally, look at other people's projects, and don't be too insecure to ask folks for help.
Excellent. Well, thank you so much for your talk today, Zach. It was just amazing, and all the answers to the questions. On behalf of Hope 2020 and all our attendees and presenters and volunteers, thank you. So with that, come back at the top of the hour for our next talk, Borders and Biometrics, Boundaries of Computer Vision with Charlie Myers. Until then, keep on hacking. Take it away, Hope Ground Control.